My dear students, welcome back to our channel. In this video, I will be explaining the BCA first semester subject Mathematical Foundation of Computer Science, MFCS, as prescribed by Osmania University and other universities of Telangana. We will go through the important questions and answers one by one. Let's begin with a quick revision. Unit 5 first important short question is: define the complete graph with example. A complete graph is a special type of simple graph in which every vertex is connected to every other vertex by exactly one edge. This means no two vertices are left unconnected and there are no repeated edges. A complete graph with n vertices is written as K. It contains n1, 2 edges. This formula comes because every vertex connects to all the remaining n1 vertices. Easy way to remember. Think of a group of friends where everyone knows everyone. Since each person is connected to every other person, this forms a complete graph. Example: consider K, a complete graph with 4 vertices A, B, C and D. A connects to B, C and D. B connects to C and D. C connects to D. Total edges is equal to 6. Graph looks like a fully connected square with both diagonals drawn. Thus, K is a complete graph because all vertices are linked to each other. Next important short question is: to define direct and non-direct graph. A directed graph, also called a digraph, is a graph in which every edge has a direction. This means the connection goes from one vertex to another, like a one-way road. We show a directed edge using an arrow. Example of directed graph. If there is an edge AB, it means you can go from A to B, but not necessarily from B to A. A non-directed graph, or undirected graph, is a graph in which edges do not have any direction. Connections work both ways, like a two-way road. We show an undirected edge using a simple line. Example of undirected graph. If A, B, you can travel A to B and B to A freely. Easy way to remember. Directed is equal to one-way road, arrow. Undirected is equal to two-way road, simple line. Both graphs help us model networks like roads, social networks, and computer connections. Next important short question is: 3. A simple graph has 10 vertices and 21 edges. Find total edges in its complement. A simple graph has 10 vertices and 21 edges. Find total edges in its complement. To find the number of edges in the complement of a graph, first remember. Formula for edges in a complete graph. A complete graph with n vertices has n1, 2 edges. Here, n is equal to 10. So total edges in K is equal to 10, 10 to 1, 2 is equal to 10 times 9, 2 is equal to 45. This means a graph with 10 vertices can have a maximum of 45 edges. Complement of a graph. The complement contains all the edges that are missing in the original graph. Step by step. Maximum possible edges is equal to 45. Actual edges in the given graph is equal to 21. Missing edges is equal to 45, 21 is equal to 24. Easy way to remember. Complement edges is equal to maximum edges present edges. Final answer. The complement of the graph has 24 edges. Next important long question is: 4. Draw all distinct binary trees with 4 vertices. A binary tree is a tree in which each node can have 0, 1 or 2 children. With 4 vertices, only 5 distinct, non-isomorphic, binary trees are possible. We change the structure not the labels. Below are the 5 different shapes. 1. Skewed right tree. A, B, C, D. 2. Skewed left tree. A, B, C, D. 3. Root with 2 children. Left child has 1 child. A, B, C, D. 4. Root with 2 children. Right child has 1 child. A, B, C, D. 5. 1 child on left, then right. A, B, C, D. Easy tip. Think of these as all possible ways to arrange 4 nodes without breaking the binary rule. Next important short question is 5. Define rooted tree with example. A rooted tree is a special type of tree in which one vertex is chosen as the root. From this root, every other node can be reached through a unique path. The root helps us define parent, child, ancestor, descendant, and levels in the tree. How it works? The root is the topmost node. Every node, except the root, has a parent. Nodes connected below a parent are called children. Levels tell how far a node is from the root. Example: R, A, B, C. Here, R is the root. A and B are children of R. C is a child of B. Levels: R level 0, AB level 1, C level 2. Easy way to remember. A rooted tree looks like a family tree, where the root is like the grandparent and all others grow downward. Next unit 5. Long questions. First important long question is: define the following terms with diagram. 1. Direct graph. 2. Self-loop. 3. Parallel edges. 4. Adjacent edges. 1. Define the following terms with diagram. 1. Directed graph. 2. Self-loop. 3. Parallel edges. 4. Adjacent edges. 1. Directed graph, digraph. A directed graph is a graph in which every edge has a direction. Edges are drawn using arrows, showing the movement from one vertex to another. It is like a one-way road. Diagram: A, B, C. Example: edge AB means you can go from A to B, but not necessarily from B to A. Easy tip. Directed is equal to arrow is equal to one-way route. 2. Self-loop. A self-loop is an edge that starts and ends on the same vertex. It shows that a vertex has a connection to itself. Diagram: A. Example: if a computer sends data to itself, this can be modeled using a self-loop. Easy tip. Self-loop is equal to self-connection. 3. Parallel edges, multiple edges. 2 or more edges that connect the same pair of vertices are called parallel edges. They show more than one connection between the same two nodes. Diagram: A is equal to B. Example: two roads connecting the same two cities represent parallel edges. Easy tip. Parallel edges is equal to more than one route between same vertices. 4. Adjacent edges. Two edges are said to be adjacent if they share a common vertex. Diagram: B, A, C. Here, edges AB and AC meet at A, so they are adjacent. Example: if two roads start from the same junction, they are adjacent edges. Easy tip. Adjacent is equal to edges touching at a point. Final memory trick. Directed graph arrow one way. Self-loop circle on same vertex. Parallel edges double line between two vertices. Adjacent edges meet at same vertex. Next important long question is: 2. Write a brief note about the basic rules for constructing Hamiltonian cycles. A Hamiltonian cycle is a special type of cycle in a graph that visits every vertex exactly once and finally returns to the starting point. While constructing a Hamiltonian cycle, we must follow some basic rules or guidelines to ensure we form a correct cycle without missing or repeating vertices. 1. Visit each vertex exactly once. This is the most important rule. You cannot repeat a vertex except the starting vertex at the end. Hamiltonian cycles work like visiting all friends once and returning home. 2. Do not repeat any edge. Every edge should be used only once. Repeating edges would create unnecessary loops and break the Hamiltonian property. 3. Start and end at the same vertex. The cycle must return to the starting point, forming a closed loop. If it does not return, it becomes only a Hamiltonian path, not a cycle. 4. Avoid forming small cycles early. While connecting vertices, avoid creating a closed loop before all vertices are included. A small cycle blocks remaining vertices from joining the main cycle. Example: if you form BCA too early, remaining vertices can't be added. 5. Ensure no vertex becomes isolated. While picking edges, make sure no vertex is cut off. Every vertex should have at least 2 connections, degree greater than or equal to 2, in the final cycle. 6. Choose edges that help continue the cycle. While constructing step by step, choose edges that allow the cycle to proceed forward without creating dead ends. If a vertex leads to no further edge, the cycle cannot be completed. 7. Use simple conditions, optional. Some theorems help quickly check whether a graph may have a Hamiltonian cycle. Dirac's theorem: if every vertex has degree greater than or equal to n/, to the graph is Hamiltonian. Ore's theorem: for every pair of non-adjacent vertices u and v, if they u plus they v greater than or equal to n, the graph is Hamiltonian. Easy memory trick. 1 visit, 1 edge, 1 loop at end. No small cycles, no isolated nodes. Next important long question is: 3. What is a Hamiltonian graph? Explain with an example. A Hamiltonian graph is a graph that contains at least one Hamiltonian cycle. A Hamiltonian cycle is a special closed path in which 1. Every vertex is visited exactly once and 2. The path returns to the starting vertex. If a graph has even one such cycle, it is called a Hamiltonian graph. Definition in simple words: a Hamiltonian graph is like a trip where you visit each city exactly one time and finally return to your home city without repeating any city in between. If such a tour is possible, the graph is Hamiltonian. Important points: no vertex should be skipped. No vertex should be repeated. Only the first and last vertex are allowed to be the same. Edges cannot be reused. Hamiltonian cycle must cover all vertices. Example of a Hamiltonian graph. Consider the cycle graph C with vertices A, B, C, and D. A, B, D, C. Let us check if it has a Hamiltonian cycle. One possible cycle is ABCDA. This cycle satisfies all conditions. All vertices A, B, C, D are visited once. It returns to the starting vertex A. No edge and no vertex is repeated. Since this graph has a Hamiltonian cycle, C is a Hamiltonian graph. Another example, slightly bigger. Consider a pentagon, 5-sided cycle, C. ABCDEA. This also visits every vertex once, so C is Hamiltonian. Non-Hamiltonian example, for contrast. A graph shaped like a T cannot have a Hamiltonian cycle because one branch ends at a vertex with degree 1, and you cannot return after visiting it. Easy memory trick. If you can make a round trip touching every vertex exactly once, the graph is Hamiltonian. Next important long question is: 4. Determine a railway network of minimal cost for the cities in the given figure. When we have several cities connected by railways with different costs, our goal is to connect all cities using the minimum total cost. This problem can be solved using minimum spanning tree, MST, from graph theory. Step 1. Represent the network as a graph. Cities is equal to vertices. Railways is equal to edges with costs as weights. Example: cities A, B, C, D. Railways with costs A, B is equal to 4, A, C is equal to 2, B, C is equal to 5, B, D is equal to 10, C, D is equal to 3. Step 2. Choose an algorithm. 2 popular algorithms for MST. 1. Kruskal's algorithm. Pick edges in increasing order of cost, avoiding cycles. 2. Prim's algorithm. Start from any vertex and add the cheapest edge connecting new vertices until all vertices are included. Step 3. Apply Kruskal's algorithm. Step-by-step example. Edges in increasing order. C, D is equal to 3, A, C is equal to 2, A, B is equal to 4, B, C is equal to 5, B, D is equal to 10. 1. Pick A, C, 2, add to MST. 2. Pick C, D, 3, add to MST. 3. Pick A, B, 4, add to MST. At this point, all 4 cities are connected. Total cost is equal to 2 plus 3 plus 4 equals 9. Edges B, C and B, D are ignored to avoid cycles. Step 4. Draw the MST. A, B, C, D. All cities are connected. Total cost is equal to 9 minimum. Easy way to remember. Connect all cities using the cheapest edges, but don't form loops. Cheapest first Kruskal. Grow from one city prim. Both methods lead to the minimum cost railway network. This approach works for any number of cities. Once you have the figure, just list edges with costs and apply the steps above. Next important long question is: 5. Discuss spanning trees and minimum spanning trees. 1. Spanning tree. A spanning tree of a connected graph is a subgraph that 1. Includes all vertices of the graph. 2. Has no cycles, it is a tree. 3. Contains exactly n1 edges if there are n vertices. Key points. A graph can have many different spanning trees. Each spanning tree connects all vertices without any loops. Spanning trees are useful in network design to ensure full connectivity with minimal structure. Example. Consider a graph with vertices A, B, C, D and edges A, B, A, C, B, C, B, D, C, D. One spanning tree could be A, B, C, D. Edges in this tree A, B, A, C, C, D, 3 edges for 4 vertices. No cycles and all vertices are connected. 2. Minimum spanning tree, MST. A minimum spanning tree, MST, is a spanning tree with the smallest total edge weight among all possible spanning trees. Key points. MST is used when edges have costs weights, example, railway lines, communication networks, or power grids. MST helps minimize total cost while connecting all vertices. Algorithms to find MST. 1. Kruskal's algorithm. Pick edges in increasing order of weight, avoid cycles. 2. Prim's algorithm. Start from a vertex, and the smallest edge connecting a new vertex until all vertices are included. Example: graph with vertices A, B, C, D and weighted edges. A, B is equal to 4, A, C is equal to 2, B, C is equal to 5, B, D is equal to 10, C, D is equal to 3. Steps using Kruskal's algorithm. 1. Pick smallest edge A, C is equal to 2. 2. Pick next smallest C, D is equal to 3. 3. Pick next smallest A, B is equal to 4. MST edges A, C, C, D, A, B. Total cost 2 plus 3 plus 4 equals 9 minimum. Easy way to remember. Spanning tree connects all vertices without cycles. Minimum spanning tree, same, but total cost is minimum. Think MST is equal to cheapest way to connect all points.